Hello, I'm audible. सुनते ही सब उसके बाद है मतलब Hello guys. Today we'll be discussing today's Go for Gold ICPC contest. One sec. Uh, yeah, we'll first be discussing problem H. It was a relatively very simple problem. So in this problem, we were given some of the constraints and we had to uh, print the we have to decompose these constraints in the minimum number of constraints possible. So for example, let's see this test case. So we were given that so this operator means or and this is and so the first constraint says that our x should lie between 5 and 10. Second says that it should be between 7 and 20, and the third says it should be less than or it should be less than equal to 2. Fourth says it should be greater than equal to 21 and less than equal to 25. So let's say it's 25. So something like this. And then between 8 and 10. So something here. And then greater than equal to 100. So we need to just print the union of these constraints. So for example, for this range between 5 to 20, we can decompose all of these uh, constraints in a single constraint. That is to say that x lies between 5 to 20. Now we can also union it with the 21 to 25 constraint to make this new constraint 5 to 25. So the first constant has to be something like minus infinity to 2, 5 to 25, and 100 to infinity, right? So this is what we had to print. X is less than equal to 2, or x is greater than equal to 5, less than 25, or x is greater than equal to 100. So, right. And we had to print true when all of minus infinity to infinity range of integers x satisfy these constraints. So x greater than equal to 0 and x less than equal to 10. So it's something like x has to be less than equal to 10 or x is greater than equal to 0. So Yeah. Uh, yeah. Sorry for the technical difficulty. So now we've given this example x greater than equal to 10 and x less than equal to sorry x less than equal to 10 and or x greater than equal to 0. So this these constraints encompass our all of our integer values. So, so hence we'll print true in this case. And now uh, it was given that the set of integers given to us in the problem will lie between minus 2 to the power 15 to 2 to the power 15 minus 1. So we can just set 2 to the power 15 as our infinity value, and we'll just continue with our code. So now, how to solve this problem? You just so the difficulty was to parse the string. So you'll get line. You'll use this command. So you'll input this whole string in the variable s, and now you'll maintain uh, disjoint unions of intervals, and whenever you're adding a new interval, so these disjoint unions, these disjoint sets will be stored in a set, and whenever you'll be adding a new, whenever you'll be adding a new this interval, say something like this. So you'll binary search in the set, use lower bound function, and find the smallest uh, segment that is just greater than find the smallest segment that has L greater than equal to your insert current L that is to be inserted. And then now as all of these segments are disjoint, so at most, so there can be at most one segment that has uh, its R greater than equal to L. So so basically what I'm saying is that when you will be finding the segment that is that has its L value greater than your value L, there can be at most one such segment, which is so this will be the segment that will be provided by your set, and there can be at most one segment that will uh, like union it with this segment. So you can just store these segments in a set, pair intent, and then like pop out the segments that join it with this new segment, and then finally you'll at the end you'll be having some sort of disjoint segments. It will be L1 to R1, L2 to R2, and so on. And what we'll be printing is that x less than equal to R1 greater than equal to L1, or x less than equal to R2 greater than equal to L2, or and so on. So this is what the output was expected. Yeah. So this was problem number H. Now let's move on to the next problem. Yeah, so let's move on to the problem G. So yeah, so so in this problem we were given uh like we were playing a Jenga, like Jane is playing a Jenga game. Uh, so there are each row of this Jenga has n Jengas. So n, let's call them okay, let's call them a block. So there are n blocks in each row, and the height of Jenga is given as h. So you'll be given n. Yeah, so n is our number of blocks in each row, and W is the width of this Jenga. So this is W, and this is the height of the Jenga, and you're also given M moves. So in each move, you'll be given the level at which you're going. So each move is characterized by at the level you're going, and the K is the uh, block that you're removing from that level. So for example, for this test case, so there will be 5 Jengas in each row, and the width of each block is 2, uh, and 6 is the height of the Jenga, and 6 moves you'll be given. So in first move, you remove 4 from the fourth level. You remove the first block. So you go to the fourth level to remove the first block. So this is first, this is second, this is third, this is fourth, this is fifth. So you remove the first block. In the second move, you remove the second block. So this one gets removed. In the third move, you remove the fifth block. Right. In the fourth move, you go to fifth level and remove the third block. So you go to fifth level, remove the third block, this one. And in the fifth move, it's 4 comma 3. So you go to the fourth level and remove the third block, this one. Now note that this is the same figure as given to your right. So when you remove the third block, the Jenga falls down. So we have a condition that is given that the tower collapses if there is a cross section between levels such that the center of the mass of the levels above it does not belong to or so uh yeah, one second. So you're given a Jenga, right? So it says that the tower topples when there's a cross section between levels. So let's say this is some level k plus 1, this is some level k. So the tower topples when there is the center of, so we have some levels above it as well. So when the center of mass of all the above levels, so uh, let's let's call this as x-axis, and let's call this as y-axis. So as you can see, the center of mass, like all the levels above, so all the levels above level 4, levels 5 and 6, will have some center of mass of the Jenga. So it says that when the center of mass of the levels above the current level is either at the edge or outside of the convex hull of the previous level projection. So this has some center of mass which is going down. So at level 4, when you remove this block, so what exactly are we saying by the convex hull? So suppose let's look at a particular level. So uh, okay, in this example itself, the convex hull is said to be something like this. So it says the projection of the previous level, right? So this is a convex hull of our this particular state. So the convex hull like it's basically a projection of your current state. So if you had so basically let's say in horizontal level you had some blocks, some you had some block here, and let's say you had the leftmost block as here, right? So the convex hull is nothing but like the projection of this level. Okay, so when you see it from the left, the first thing you see is at some distance I. When you see from it, when you see it from the right, the first thing you see is the first block itself, right? So the we can define the projection of each row. So projection of each row is characterized by some L comma R, right? Where L is the a number of consecutive blocks that are removed from the left end. So in this case, suppose there were three blocks that have been removed from here. So this is, let's say it 1, 2, 3, and so on till n. Let's say nth block was removed, n minus 1th was removed, n minus 2th was removed. So L is n minus 3 in this case, and our R is in this case 1. So projection of each row is characterized by L comma R. So L is the first instance of the block from the left end, and R is the first instance of the block from the right end. So in this case, for the third row, our our projection will be defined as so let's take L as a smaller one. So it would be 3, comma from the right end it would be 5. Sorry, 4, because 1 was removed, right? So when this gray area is removed, it is 3 comma 4. So now what can you say about topple here? So for a current row, you have some L comma R as a projection. So it says if your CUM either goes down from here or it goes down from here, then uh, then it topples, or it just grazes this as well. So okay, so this is what the question was. And now to solve this problem, what you can do is, so note that H and M is less than equal to 5,000. So you can, so basically for each move, 1 to M, you can, let's say you're removing kth block from lth level, and you'll, so uh, you'll maintain a vector set for each level. This will store this will store all the blocks that are removed at each level. So in the lth level, so you just iterate height from h to 1, and you just check if a condition of toppling is getting satisfied at this point. You have to output the first instance of the move when the when the uh, this Jenga topples, right? So for each height, you check if it topples. So you can just calculate the COM of all the above blocks, which is just by normal COM formula of sum of x coordinates of mass of Jenga upon the count of x coordinates, and similarly for the y. So you have a COM x coordinate as well as COM y coordinate, and you can just check if this uh, so and for each height you have using this set, you have its projection as well, L comma R. So if this COM x is less than equal to L, or COM y is greater than equal to R, then it sort of topples. So there are also some implementation, like you need some precision in implementation as well. And W here, the width is just irrelevant. It is not like required here. So this was more or less this problem. Yeah, so we'll move on to the next problem.
So in this question, we basically had a few cards, and we chose a random variable uh, k uniformly between 1 and n, and we take the top k cards from the stack, and we turn them over on the basis of the first card which is there. So let's say for the first test case CWCC, so if we have the number random number chosen as 2, so like we will select these two cards, and then since this first card is correct, we'll keep them aside and then work on with these remaining two cards CC. So since our goal is to calculate the expected number of wrong cards uh, after the process has been completed, uh, let us define FI as the expected value, which expected value of wrong cards, which comes when we have like let's say all the cards remaining from I to N. So so we will define our like FI as uh, like let's say our k cards are remaining, so from fi plus 1, rather our iteration will be from I plus 1 to n, and we will get like f of j, that is the expected value of cards which will be remaining after we have removed some of the cards. And apart from this, there will be a additional term which will be the number of cards which are wrong in the currently selected interval. So like we can represent like our expected value as sum of these two, and we can calculate the expected value as in them each expected value independently. So like uh, for the last card, if we have a wrong card, then f of n will be 0, irrespective of whether it is a wrong or correct card, since we will correct the card if it's on the top of the stack. So for uh, n minus 1 onwards, uh, we will take the like maintain a summation of the FIs from I plus 1 to n, and also like we will maintain a prefix sum of the like wrong cards. So let's say we have a pre of I, which is summation of like indicator variable whether the current uh, card is a wrong card. So that will be our prefix sum, and through it we can calculate the values in the interval, and each of them can be done independently. So that can be done by maintaining sums. So moving on to the next question, uh, it's problem G, the game on graph. So in this problem, the player Gennady tries to prioritize a strategy in which the game goes on infinitely, and like the other player prefers the termination of the game, that is winning or losing, uh, over uh, the game being infinity. So, like, we can first uh, think of the problem as like determining whether the game will terminate or not, considering that the first player wants the game to continue always and the other player wants it to terminate. So, uh, in this question, the all the vertex which have their out degree to be zero uh, will have like their when we are on them, the we always know that it will terminate. The game will terminate. So for all other vertices, we will do something similar to topo sort. So, like, let's say we have a queue of all vertices which have their out degree as zero, and then uh, for each such vertex, we will consider all the vertices which are falling on it, and for these vertices, so like we also need to do this for each of the players. One player will try to terminate the game, and other will try to like continue forward. So let us define the AI of like where A is player A and I is the ith node. So it is 0 if player A is able to like not able to continue the game always. So that means it will terminate, and one if he's able to continue always, and the player B I will have 0 if he's not able to terminate the game, but 1 when he's able to terminate the game. So for the like all nodes which have out degree as 0, they will have their AIs and BIs set to 0. So, like, considering the all the edges, let's say we create a copy of each edge, which represents the node if the game is starting with respect to A, and like let's say there is a node I, so it will have IA and IB, two copies of the node, and all the edges from I to J will be from IA to JB and IB to J. So we'll construct these edges as corresponding to the new nodes, and then uh, whenever the uh, out degree of any node is 0, we'll add it to our queue. So let's say there is a node IA, and it has multiple edges to, let's say, 1B, 2B, and so on. If we know that game will terminate for all these, uh, like even if there is one vertex 1B on which game terminates, we will know that the game will also terminate on IA if A wants to them to terminate, as it can move to the that edge. And if we have player like B who doesn't want to terminate, then for that player uh, the value will terminate only if all its outgoing edges are like 1A, 2A, all of these are terminating, then only uh, IB will terminate. So like we can differentiate whether a person wants it to terminate or not terminate, and then we can apply a similar procedure moving forward by like discarding those edges which don't follow on like terminating node to terminating node. We'll only keep those edges which are there from a particular terminating node to another terminating node, and we can apply the same concept to find the winning and losing moves.
So this is question A, and the question statement says that abbreviated sequence of words is a sequence of capitalized words. A capitalized word is given in the question that it is a starts with an uppercase character and followed by all the lowercase characters only. So an abbreviated sequence is a sequence of capitalized words and separated by exactly one uh, space, white space. So now in the every line one we have to find the abbreviated sequences. Like in this Northeastern European regional contest was an abbreviated sequence. So we write it as NEERC, and in that and next to that with one space we write the Northeastern European regional contest. So what I did was that I started parsing the string, and uh, first of all, I made a vector, and in that I made a flag that it is a capitalized string or not. So when it is a capitalized string, so I checked if the when it is a capitalized string, I checked if next to that if next to that is a white space, and also it is a followed by a capitalized string or not. If it is a capitalized string next to that, so we also take that string and we keep on concatenating the first characters of that string, and when the sequence of capitalized characters end, we write we first concatenate the uppercase characters and then followed by one space, and then with brackets we write the string. So this is what I did for this question. So let's move on to question E. in question E, it says that every person joins the queue and it is marked by minus when a person demands for a cycle on time t and the number of cycles. So in this test case, we can see that and also whichever person in the queue at the front gets a cycle, he moves out of the queue and he gets the cycle, how many cycles he has. So here it is that minus 1, minus 1 1, minus 2 2, plus 4 1, minus 6 1, and plus 7 2. So here he demands one cycle at time 1. Here it and the total demand of cycles is time cycle 3 at time 2. Now they get one person gets a cycle at time 4. So now there is a demand of 2 cycles. And at time 6 there is a demand of 3 cycles, and then at time 7 they get 2 cycles. So one cycle is left and a person is not satisfied. So we print infinity. Now in this, we can see that in between two consecutive timestamps, if the prefix sum is negative, that means that the number, the absolute of that number is the count. Is the count means two people has not been satisfied, because the prefix sum tells that minus 1 minus 2 plus 4 means minus 1. So one person has not been satisfied. Similarly, for we can do for minus 2. So now what we have to do, like between any two consecutive timestamps, we have to find the prefix sum before that. So and the wait time will only be there when we get a negative prefix sum before that timestamp. So we first compute the prefix sums, and now we store it in a pair of vectors, vector of pairs. Okay, vector of pair. First we store in the vector of pair the prefix sum and then the difference of the timestamps. Now difference of the timestamps. So now we sort this vector. Now in the initially, if there are b cycles, the our use case is only of those cycles which are negative, because they will only add to the waiting time. So when we add b cycles at the start, only the prefix sums with which are less than minus b will be of our use. So we first sort them, since we have the sorted vector of prefix sums with the timestamp as the second element. So initially we have to also compute the sum of timestamps till a particular index, and also the answer, which is the sum of times, which is also the product of timestamp difference into the absolute of the value, because this is the absolute of value gives us the count of the people who are waiting, and the timestamp difference tells us the amount of time for which they are waiting. So their product gives us the total amount, and we have to store their sum. Now we have to store their sum. Now when a particular b comes, our use case is only of minus b. So we also calculate till a particular index the sum of the timestamps in the sorted array. Now we apply binary search and find the first element. We find the last element which is less than minus b, and we have the prefix sum of the answers with them. Now we add the product of the sum of timestamps and the prefix and b, and then and this gives us the total timestamp for every query waiting time. Now let's move on to question b. This question is a standard two-side question with which we have to implement with trials. in this, see, there is at most one question mark in every string. So there are at most two n strings. Like for every string, we get two strings. So in the try, we first insert, we find out for every string, we mark its end, its leaf, and we mark its leaf on the try, on the graph, on the try graph. And when we apply DFS, we apply the standard small to large merging algorithm until and at a point, whatever points we get in a vector, the negation of that we mark in the two-side graph as edges. And after this, we can apply the standard two-side algorithm to get the answer. So this was the answer for question B. The question D says that every cat must be sleeping or eating in an hour, and between every k hours there must be at least ms timestamps at which the cat must sleep and at least me at which the cat must eat. So this min of e we get is equal to me, and the max of e is equal to k minus me. Similarly, the min of s, now we can see that we can write it as summation of si, since we want to find keep only one variable and rest as the difference. So we can write it that summation of si, the overall sum for every, and then delta I into si minus into ei minus si. This delta I will be one only in some cases in which the cat eats, and this gives us now as we get a feel of dynamic programming. But this is a, as we have seen in many questions on CSES also, that dynamic programming questions we can when we don't get the constraints which we can solve, so we can move towards the maximum flow question, min cost max flow question. Okay, so like fi is the maximum amount of delight for hours from I to n. So let's take the case when min e is equal to 0 and max e greater than equal to 0. So we can see that for vertex I to I plus 1, see, min e is equal to 0. So we can keep the cost as 0 because nothing is added, and the capacity as maxi, since there can be at most maxi flows in that in an from the start. Like in the initial we mark S and T as the sink and source nodes. So from the source, we if we flow at most maxi, that can only be flown from I to I plus 1, because marking it as maxi times which has been eaten in an interval. So and the cost is 0 in that, since no. So and also we can take from I to I plus k the capacity of 1 by marking it as sleeping because of with cost of minus delta I. So we have to find the negative minimum cost negative minimum cost of flow of value max C. At the last, since we will report minus then the answer will be summation of Si plus delta I. So we will take the minimum and then the negative of that. Now similar to this case is the case with mini, because we can take, because we can mark mini e. We have to take for every interval just maxi minus mini for I to I plus 1, means we must have I mini elements in the k hours sleeping before. So we mark it I to I plus 1 with maxi minus mini and I to I plus k with capacity 1 and cost of minus delta I. So the negative minimum cost flow of value maxi from S to T will give us the answer, and we have to just add it with summation of Si plus the my negated minimum cost flow. That gives us the answer. So thank you for this session.